Ampere's Law 2. A thick wire of radius r is shown. The wire carries a current with a uniform current density J throughout the wire's cross-section. Derive expressions for the magnitude of the B field for, firstly, little r less than big R, and secondly, for little r greater than big R. At the end, graph the results. Let's review current density here briefly. Current density, you recall, is the current per area. And when it says that J is constant here, that means that every little tiny bit of this cross-section carries the same amount of current as every other bit. There isn't a greater concentration of the current, say, at the center compared to the outside. To find the magnitude of a magnetic field, we are going to be using Ampere's law. For r less than big R, we need to draw an Amperian loop. There's an Amperian loop right there, where that distance is little r. It's got to be less than big R. And Ampere's law says that mu naught times the current that is enclosed should equal the integral of B dot dl. Mu naught is a constant. What is the current that's enclosed here? The current that's enclosed, if we look at that equation that's at the top of the page, you see that? The current that's enclosed is going to be the current density, which we know, multiplied by the area of that portion. For this case, the current density multiplied by the area. Now, what's the area within this little Amperian loop? See, the current that's on the outside is not enclosed. So the only current we need to worry about is what's inside here. What is that area? That area is pi little r squared. That's the area of that loop. Now, on the right side, we're never concerned about the area of the loop. We're only concerned about its circumference. At that location of r, b is a constant, which means it can be pulled outside the integral, which means we need to integrate dl. And basically, anytime you integrate dl with Ampere's law, in this class anyway, it's pretty much going to end up as 2 pi r. There is one tiny exception for that, but we'll get to that in some later videos. All right, can we simplify this at all? The pi's cancel. I think that r cancels that r right there. And so what's the magnitude of the magnetic field? What do we end up with? We end up with a 1/2 there, 1/2 mu naught IJR. IJR. No, not I. Silly Mr. Bergman. We figured out the I. The I was the J times the A. So mu naught times J times R times 1/2. We can start drawing the graph already. We can see that the magnetic field is directly proportional to R. Our graph up until big R is going to look like that, where the magnetic field is directly proportional to R. As R gets bigger, linearly with it, B gets bigger. This is in the lower left-hand corner of your screen. Now, what if little r is bigger than big R? Well, now we need a different Amperian loop. So it's going to be out here. There's little r now. We're going to use Ampere's law again, just like always. Mu naught times the I that's enclosed is equal to the integral of B dot dl. The I that's enclosed is once again J times the area that's carrying current. Now the area that's carrying current is only up to big R. It's not all the way out to little r. It's only up to big R, and then the current carrying stops. So that means that A here is going to be pi big R squared. And on the right side, that B value is going to be constant at that location of little r. We're going to integrate dl. And so when you integrate dl around the horn, you get 2 pi little r, because that's for the Amperian loop. If we simplify this, what happens here? It looks like the pi's cancel, but I think that's just about it. The mu naught and the j and the r squared still appear in the numerator, big R squared. And then in the denominator, I'm seeing a 2 and a little r, like that. What is happening here to the magnetic field as we get outside the wire? Everything is a constant here except r. So we're falling away relative to 1 over r here. If we finish this by drawing the graph, we're going to have a curve that looks kind of like that, where outside this wire, B is proportional to 1 over r. And finally, what is the direction of this magnetic field? Look at the dots in the picture. You can see that if you use your thumbkin twist and right hand rule, you point your thumb towards the camera and your fingers on your right hand curve counterclockwise. So the direction is going to be counterclockwise for both of these cases.